as Sean noted, the collaborators are Ben, who's actually a fellow from the centre, and Malcolm, who you heard this morning. I guess the whole background of this talk was well laid down this morning in that we absolutely know that climate change is a huge issue. It's actually measuring where that is going and the spatial extent of those types of effects. So what we're looking at here is the utility of fish and corals as effectively a biomonitoring tool. We can look at different spatial scales and look over different periods of time. And of course, although IMOS has just come to us in terms of remote sensing through temperature probes and all the rest of it, we don't have the history, and it's only where those probes are. So this is trying to address that problem. Now, inherent in this particular approach is using a flash toy called LA-ICPMS. It's a laser-based mass spectrometer, which allows you to take very discrete little samples across the calcium carbonate of either the otoliths of fish or the corals, as explained by Malcolm this morning. Now, certainly in the case of the fishes, we've used elemental signals to find out about the fish a lot in terms of their movements and a whole range of other things, but there have been very few applications in terms of using the otolith as a tool to tell us about the environment. So briefly, I'm going to go through some of the environmental forcing on the Great Barrier Reef, and Janice touched on this morning, some of the major issues that we might be concerned about and how this type of approach might help us out. We're going to look at the good candidates as biorecorders, what are prerequisites for this to work. I'm going to talk about upwelling and how that is recorded in fish and coral, and I'd point out that upwelling on the Great Barrier Reef is often considered an oxymoron, and you tend to think of it as the Darwin's paradox, where it's a nutrient-poor environment, and I'll focus on that to some extent. We'll then go into the inshore reefs that Malcolm spoke about with a strong freshwater influence, and how that is recorded in both fish and corals. I then want to really focus on just how good are these organisms for telling us about pulses and presses, because I think we all know that the way that climate change is working, things tend to happen over short or longer term pulses, and that's very evident with temperature, for example, on the Great Barrier Reef, where you'll sometimes find pools of water coming in for a period of days, weeks, or even months. So distinguishing those types of pulses and presses is very much a challenge, and where from here. So if you're looking for some sort of biorecorder to tell you about the environment, these are the types of things you'd look for. First of all, they deposit sequential layers of calcium carbonate, and the layers are not reworked. Of course, if you look like something like calcium phosphate, our bone, it's actually reworked, so it's no use in terms of a biorecorder, whereas calcium carbonate is normally very good. The other obvious thing would be the wider the layers are, the greater the potential is to actually resolve something to do with respect to change in the environment. And that these layers can be aged, and Malcolm already explained this morning the lovely annually laid down in something like Porites, and of course we know with fishes that they have annually and even daily rings. A good thing is the organism doesn't move, and that the environmental signal you take from the calcium carbonate is indicative of the environment as opposed to the fish whizzing around the Great Barrier Reef during the year. And also that the organism is long-lived, so that your trace is over a very long period of time. Okay, the first candidate is a territorial reef fish. It's Acanthochromis polyacanthus. These are some data from Dave Williams down the bottom here, where he's inner, mid and outer reefs and even oceanic reefs. Acanthochromis is one of the few species that you find right across the profile of the Great Barrier Reef and even into the Coral Sea. So it's a great candidate with respect to finding it anywhere. It's a good lab rat as such. They tend to brood their young, of course, and they stay in the same area for their entire life. So we're happy about the fact that these fish don't move and therefore meet that criterion. Porites, Malcolm has already introduced the joys of Porites as such. We know that these organisms lay down about 1 cent of aragonite per year and therefore provide a great opportunity for looking at environmental signals. And I'll be going to a resolution that Malcolm didn't deal with this morning. Malcolm was dealing with very long time periods. Okay, again, this is introduced very well this morning in terms of the Great Barrier Reef, inshore areas, mid-shelf and outer shelf areas. Two of the major elements of physical forcing in these areas are as follows. Upwelling. Now, as I mentioned, you don't really think about upwelling on the Great Barrier Reef, but if you look right along the outer reefs here, there are significant intrusions of cool water. And this is an image that Eric Wolanski provided showing chlorophyll signals. This is chlorophyll responding to that cool upwelling water that's coming up toward the fringing reefs of the GBR. Now, this is pretty wimpy upwelling by world standards. If you look at upwelling off the coast of California or somewhere like that, you're talking about upwelling of the order of like 15 micromoles per mole of nitrate, whereas on the Great Barrier Reef it's probably down around 3. Nevertheless, it's incredibly important biologically in terms of the input of vast amounts of material to the GBR. On the inshore GBR, we have the strong riverine influence here. This image here is showing the Burdekin plume coming out here, going all the way up past Townsville, the Palm Island group in Hitchbrook, and ski jumping here off Cairns and going something like 50 kilometres into the waters of the Coral Sea. And between these two areas here, you have lots of mid-shelf reefs, which, as I mentioned later on, are barely affected by either the rivers or the upwelling under normal circumstances. So we can look on the outside here and know the signals that we're seeing are based on upwelling and not riverine influence, and vice versa. For here, there's very little upwelling influence in these inshore areas. Okay, so the first port of call for the team was Myrmidon Reef, way out here. Here's Townsville to give you your bearings, the Palm Island group. Whoops, here we go. Getting the Malcolm disease. And you can see here, of course, that the Myrmidon is like the bow of a ship. It's sitting right on the drop-off into abyssal depths, essentially. So water is upwelling here from over 4,000 metres of water into these shallow areas. And you can actually see this type of upwelling from satellite imagery. This is provided by Craig Steinberg. Here is Myrmidon here. You can see a little puddle of green water here, which is upwelling occurring in and around that reef. Now, again, upwelling is incredibly important biologically, and for us in terms of global climate change, understanding where upwelling is occurring and the duration of that upwelling is very important in terms of monitoring change. Okay, we had temperature loggers out at Myrmidon, and to my knowledge, this is the first time this has been demonstrated. Here's a 3-year time series, and the data beyond that show exactly the same, is that you can see here the seasonal cycle among years. We have something like a 6-degree difference between winter and summer. We're going from 24 degrees in this case up to about 29. What I want you to note here is that during the period from about September through the summer and right up into early autumn, there are these huge deviations. Now, this is occurring within a day, okay? Now, this is a 3-degree difference in temperature occurring within a 24-hour period. So you're getting half the seasonal cycle in terms of variation over short periods of time. Now, these events constitute large upwelling events that are impacting on the Great Barrier Reef and arguably are a huge source of nutrients to the entire ecosystem. So what we're intrigued about is whether the corals and the fishes would actually show this type of signal in the aragonite, where you'd be desperately sad if you couldn't find that type of signal if it was going to have any use at all. Now, these signals are persistent at different spatial scales. I'll just show you 2 sites that are separated by hundreds of metres here, showing very, very similar signals off Myrmidon Reef. Now, if you look at the nature of the water column in and around Myrmidon, it is as follows. Here we have, this is a depth profile here down to 300 metres. We've dropped a conductivity, temperature and depth device off the side of a bit of a Shelby Wright boat here, and we've lowered it right through down the water column. You can see here that the temperature difference between the surface and down to about 250 metres is almost a 10-degree change. And there's a very strong thermocline about here. We also sampled the water at different depths down to 150 metres. And what you can see here is a strong barium signal. This is barium, which is a trace element that is strongly indicative of upwelling. And so what you can see is as you go right down to here, you have barium-rich waters. So it was our hope that the temperature deviations you could see in the coral would manifest, in the temperature samples would manifest themselves in the coral and fishes as strong barium signals. Okay, now we already knew that barium was very rich in the bones of fishes, for example. Here's some data that we published earlier on this year for Acanthochromis, sampling at Myrmidon compared to the Inshore reefs here, and you can see in 3 separate years that Myrmidon had very high levels of barium in the aragonite of these fish compared to the Inshore reefs. And in fact, this is a world record. We had this lab, actually, we had the results from the JCU lab tested with a lab in Belgium, just to make sure it wasn't some wacky JCU thing. And it does indeed demonstrate it's the highest level found in aragonite. So the potential, therefore, to actually get a very detailed temporal or spatial time series with respect to upwelling was high, because we absolutely knew that was nothing to do with freshwater, because freshwater simply doesn't get that far offshore. So it's back to the drilling again, and as Malcolm showed, you've got these beautiful annuli that run through the Porites, about 1 centimetre in width. And when you looked at those samples, we're beaming some glee about this. These results are very new. We only got them about a month and a half ago. Here we have time along the x-axis here, and there are these beautiful strong signals here, which are in fact those strong upwelling events that you're finding at the end of the spring going into summer, coming through to autumn. And fortunately, they actually line up quite nicely with the change between years, which is when we would expect that upwelling. The other point is the amplitude of these peaks is changing dramatically through time, and we're yet to look at this with respect to the wind. We can see here 1998 and 2002, this period through here was marked by some of the largest El Ninos that we've experienced, and we suspect that it's due to strong thermal stratification inhibiting upwelling. So you're actually getting a history of upwelling in these areas based on what you're finding in the corals, and you can get this down to a very local scale. If you look at this in a lot more detail, zooming in, you can see here 2005, 2006, we're getting these very strong peaks during the upwelling season. So if you know that you're well away from a freshwater influence, barium is a very good signal for upwelling. We also know that there's what's called a partition coefficient, which is a flash way of saying how much more barium is in the coral rather than the water. We know from that the levels estimated from the coral, 2 to 6 micromoles per mole, is very similar to what we actually measured in the water. So we're pretty happy that the levels measured in the coral are about right. So for coral, strong periodicity in the barium ratios, strong correspondence with time of year when the upwelling is taking place, and there's some suggestion of a lag, which I'll talk about a bit later on. It's actually partly due, we think, to tissue absorbance, where it may delay it by a period of weeks. Now, moving on to Acanthochromis, does this show the, you can see here there's no shortage of them. What we did in the Acanthochromis is we did a cross-section of the otolith here. This is the core when the animal was born. This area here is probably when it's immature. Here's the first annulus and the second. We did a laser track right the way across here. So here on the graph, the core of the otolith, and you get way out to here before you get the first annulus. Then what we found is again these lovely peaks here, once again corresponding with these strong barium signals that relate to the upwelling taking place. Importantly, you see the first peak is by far the biggest, and the increments tend to be wider here and you're getting better resolution, and we're looking at this in terms of resolving whether you can look at the intensity of upwelling based on the size of that peak. Here's a 2-year-old. Once again, here's the core, annulus 1, annulus 2 showing these strong peaks. And here's a 1-year-old showing one strong peak, as you would hope. Okay, now comparing the fish with the upwelling intensity, we've yet to analyse these data a lot more carefully, but the size of the peak in the fish, the first peak, seems to correspond with the highest peaks that we're finding in the coral. So we think that in the coral and the fish, we can actually get a level of the level of upwelling that's taking place in these areas. So for Myrmidon, fish showed a similar pattern to corals, and this reflected the seasonal pattern of upwelling. The amplitude of peaks in fish, especially for year 1, we think can actually reflect the amplitude of upwelling. Now moving inshore to where, as Malcolm showed before, the influence of fresh water is substantial, and here's one of those puddles here. This is the Herbert River. The plume of the Herbert River coming right out into the bay, not far from Orpheus Island, giving you some indication of the amount of fresh water can come out here. Here's Havana, and one of the sets of islands that we're collecting samples of fish and corals, and it's about here that Malcolm had his very long-term coral bommies going right back to before Captain Cook arrived. And this is the position of the Palm Island group here. Okay, now we've been measuring concentrations of barium in the water here. This is a result of 3 sites and 2 replicates. And you can see here that if you look through time, every summer we're getting these very strong barium peaks. So as Malcolm explained before, as rivers flood out into the open ocean, you get complex molecules breaking down, releasing free barium, and that we can measure very well in the water. And what we're hoping here is this will be reflected in the corals and fish. This here is the flow of the Burdekin and the Herbert rivers. Okay, so if we look in these corals, once again drilling, this is at Pandora Reef, and if you look carefully, you actually see little Porites bommies right through here, some of the ones which we drilled. On the y-axis here, we have barium, and here we have megalitres per day from the Burdekin River. And what you can see here is the very strong signal in the corals and the Burdekin outflow beforehand. Now, you can see there's considerable lag taking place here. So what's actually going on? And that is very obvious from here. There's a little movie. We can see the Burdekin flowing here. And here's a time clock during one of these big freshwater events. You can see here we're up to about 24 days. So it takes almost 30 days now to actually reach the Palm Island group. Now these events, this particular event lasted 80 days. So you can see why you're getting this substantial lag between the release from the Burdekin and where you're actually finding it in these corals around here. So the Burdekin is explaining a significant part of that signal in the corals that we're finding. Okay, and similarly for the fish, once again, if you look at these little guys, a transect across a 4-year-old, where we have the core here, all the way out to year 1, we're seeing a very strong signal, and all the way out to here, multiple years, we're getting these strong barium signals. Once again, the first year appears to be the most useful in terms of measuring the actually magnitude of these types of events. The good thing is, you know that corals aren't found everywhere, but these fish are, so you've always got an alternative for the corals. And here's a little 1-year-old, again showing a very strong barium peak. So for nearshore corals and fish, we have regular pulses of barium into coastal waters that vary in amplitude, and that's very obvious over the last couple of years. We had very heavy rainfall. We find these pulses in both the corals and the fish. And there are some time delays that are very obvious, which are explained by riverine flow. In the case of the Burdekin, it's taking some of these events lasting 80 days, and it's taking over a month for the water to really have a major impact on the corals. In addition to that, the separation from the shelf, the inner parts of the reef to the offshore areas of the reef, means you can differentiate between upwelling events and fresh water. If they're both close together, they'll obviously be confounded. So for example, here you can see that here's the sampling at the inshore reefs. You absolutely know that's the freshwater influence. We have temperature loggers out here which are deployed to actually detect any cool water intrusions, and we don't pick them up in the same way that we do on these outer reefs here. So you have a very clear upwelling signal in your corals and fish out here, and a very clear freshwater signal in your corals and fish here. The good thing is they're cheap loggers, they're found absolutely everywhere, and you can use them depending on the question that you have. Okay, but how good are they in terms of pulses and presses? Obviously that actually requires some experimentation. And what we have here is, can we distinguish between pulses that are only days long or those that are weeks long? And what we're doing now is we're actually doing experiments with the fish to actually look at the duration of these pulses to see how good we are at detecting what's going on. What we already know is that we can pick up pulses as long as the 1998 El Nino event, which lasted something like, the major pulse is something like about 3 months, where there were major changes. If you're getting down to the scale of days, it's probably far too crude for that. So in summary, corals now as a fish record variation upwelling and riverine flow on a scale of months. The size of events is also reflected, but requires better calibration. We're very confident, certainly in the corals, that we're getting variation there. Long time series can certainly be gained, and this can be spatially explicit with respect to distance across the reef and along it. So your carbonate, therefore, is a really fantastic natural logger of what's going on out there. And with experimentation, we can get a much better handle in terms of the resolution of pulse and press events, because this is what we're going to be dealing with over the next few years as we get changes in phenomena like upwelling, temperature, and that type of thing. Okay, we'll leave it there.